Channel. We are taking off from where we stopped on our last session on partial differential equation. So we treated how to solve partial differential equation by direct integration, and we treated how to solve partial differential equation by separation of variable. Mostly we use separation of variable for wave equation and heat equation. So now we want to see how to solve this. Use or apply separation of variable to solve the heat equation. So just like the wave equation, the heat equation has its own general form, right? So the general form of the heat equation is d square u over dx square, right, is equal to 1 over c square du dt. If you can remember the last video we did, the wave equation was having a second order derivative here. But since this is the heat equation, the heat equation will only have a first order derivative. So now, before we start solving, just like the wave equation, we will have boundary condition and initial condition. So the boundary condition, just like our previous video, will look like this. Boundary condition: when x is equal to 0, u will be equal to 0, and when x is equal to L, u also will be equal to 0. So this can also be stated otherwise. This can be equal to any number, but mostly what we consider is when x is equal to 0, u is equal to 0, and when s is equal to L, u is also equal to what? 0. So this is the boundary condition. So we can also have initial condition. The wave equation, if you can remember the last video, the wave equation we were having two initial conditions, right? We were having when t is equal to 0, and we're having du dt, that's the initial velocity, to be equal to 0. But in this case, for heat equation, we don't need velocity, right? For heat equation, we just have u x when t is equal to 0, u is equal to 0. So for the heat equation, we're only having one initial condition. So just like the wave equation, remember, in the wave equation we consider a string, right, of length L. The head of the string is at point 0, the bottom of the string is at point L, right? Then we decided to complete it to form a coordinate axis, right? So now a displacement occurs. Now in this case of heat equation, it was due to let's say expansion and contraction. Remember, thermal expansion. So the string contracted, so that the displacement, and it formed a sag, right? A sag or a hug moment, sure. So then the displacement it forms is u, which is a function of x and t. So what we are going to be looking for in the heat equation is the value of u, how to get the u, just like the wave equation. So now the first step, let's call this step 1. Remember, for heat and wave equation, the solution of u, I call it xt, where capital letter X is a function of small letter x, and where t is a function of small letter t. Right. So now x is a function of small letter x and t is a function of small letter t. So now we are going to differentiate this in order to suit it or make it compatible with this our general form of equation. So meaning that I differentiate u. Let's say I differentiate u with respect to t, small letter t, right? So since t here is a small function of small letter t, it will affect this, right? So x is kept constant because I'm not differentiating with respect to x, I'm differentiating with respect to t. So I'll be having x t prime, right? Because we're having du dt here. So now let me create an expression too for my second order derivative with respect to x. So this is d square u over the x square, right, is equal to x prime prime of t, meaning because I differentiated with respect to x twice, right? So now I'm going to substitute the value of the expressions I got for this into the general form of my heat equation, right? So I'm going to be having x prime prime t equals 1 over c square xt prime. Now this c square is a constant, right? It can come in any form. It can come as alpha, it can come as beta, but mostly the general form was expressed as c square. So now this is my step 1, right? My step 1 is differentiating it as expressing it as this, right? And substituting back into the equation as expressing it as this. So now we apply separation of variable, right? I mean that I separate the variable for x to x and separate variable for t to t. So this will be x prime prime t this one coming here, right? So this is divided by x, right? So this is 1 over c squared t prime. So this is x, this will be x prime prime over x equals 1 over c squared, right? This will be 1 over c squared t prime over t, right? So now the third step, we introduce a constant, right? Just like the wave equation, we introduce a constant. So now let's say this is x prime prime x equals 1 over c squared t prime over t. Now let's introduce a constant k, right? So we'll be having x prime prime over x equals k, and 1 over c squared t prime over t equals k, right? So now let's express it to form a more just let's express it to form an equation with that is equal to 0. So this is or first, before we do that, we assume let k be equal to minus p square, right? Remember, this is just a step, right? Just follow me step by step. So technically, if you want, that's why I'm doing it step by step, so that you will not miss a step. So the first step we did, let me just recap. The first step we did was differentiating u with respect to x and with respect to t. So we differentiated u with respect to x, we had this. We had this. And differentiated u with respect to x 2 times, we had this. So now my third step is to substitute this into the general form of heat equation, right? And I had this, and I got this, and I arrived at this. Now my second step now was applying separation of variable. Right. So I took the one for x to x and took the one for t to t, right? So I equated the constant k, and k I'm equating it to another constant minus p squared, right? So now substitute it here. So this is let me call this step 4, right? So this is x prime prime over x equals minus p squared. This is 1 over c squared t prime over t equals minus p squared. So cross multiplying, so this is x prime prime plus p square x equals 0, right? So this is t prime equals minus c square p square t. So now these are two differential equations. These are two first order differential equations, right? So this one is second order, this one is first order. Remember, this can also be written as d square x over dx square plus p square x, right? This can also be written as dt over the small letter t equals minus c square p square t, right? So now we can solve this. Remember, if you can remember the general form for second order differential equation, for this form is given as x will be equal to a cos p x plus b sine p x. This is the solution to this second order differential equation. Why the solution to this? We can solve it like this because this is a first order differential equation. So we can solve this one using separation of variable. So this will be dt over t equals minus c square p square dt, right? Took the one for t to t and took the other one the other side, right? So now I'm going to integrate both sides, right? So integrating both sides, this is ln t, right, equals, remember integrating 1 over t, right? This is ln t. So equals minus c square p square. So integrating with respect to c, so I will be left with just t plus a constant k, right? So let me express k to be in form of natural logarithm of another constant, right? Meaning constant is a constant, right? So since we don't know the value of the constant, I can express it as another constant. That's the uniqueness of constants. If I don't know the value of a particular constant, if I say a constant is c, I can express c to be in another form. I can say let c be equal to k square. Let k square be equal to m raised to power 3. Since I don't know the value of the constant, I keep on expressing it as another expression. So the expression c. So this is ln t and ln c. So bringing this one to this other side, so this is ln t minus ln c, right? Taking this one here, this is ln t minus ln c, right? So equals minus c square p square t. So rule of logarithm says this can also be written as ln t over c equals minus c square p square t. So we stop here. Let's continue from the other page. So this is x cos px plus b sine px. So we have gotten the solution for x. We are trying to get the solution for t, right? Remember, the solution for my PDE is in terms of u, x, in terms of x and t. So now let's keep on solving. So this, remember, ln can also be written as natural logarithm to the base e, right? So this is t over c equals minus c squared p squared t. So this can also be written as, so now remember, the rule of logarithm says log to the base a of x equals b, can also be written as a over b equals x, right? So I'm going to apply the same thing here. So this can also be written as e raised to power minus c squared p squared t to be equal to t over c, right? So meaning that, let me just interchange the signs. So this is t over c equals exponential minus c squared p squared t. So this is t equals c exponential minus c squared p squared t. So this is my equation 2, right? So we've gotten the value of x to be a cos p x, right, plus b sine px. So we've completed step 4. So this is step 5, right? Step 5, we substitute it back into the general form. Remember, general form is uxt, right? So this is equation 1 and this is equation 2. So we substitute it back into this form, right? So this is u is equal to a cos px plus b sine px, right, times c exponential minus c squared p squared t, right? So now let me multiply through by the constant I have here, which is c. So let a times c be equal to d, and let b times c be equal to e. You see, I'm introducing another entirely new constant because I'm having two constants multiplying each other. Since I don't know the value of the constant, I know that is a constant, right? It's a constant I will get when I multiply two constants. So I can just assume it to be I can just replace it with another variable. So I replace it with d and replace it with e. So I can write my my solution u to be equal to u is equal to d cos px plus e sine px, right? Close bracket exponential minus c square p square t, right? So now, how do we go from here, right? So now this is where we apply the boundary condition. So now this is my step 6. So I apply boundary condition. So if you can recall, like I explained from the beginning of the video, I said the boundary condition is of this form: u0, t is equal to 0 and u0l t is equal to 0. So when s is equal to 0, u is 0. When x is equal to l, u is also what? 0. So I apply it to this equation, right? Let me apply this one first to this equation. So this is u is equal to 0 is equal to d cos p times 0, right, plus e sine p times 0, right, exponential minus c squared p squared t. Remember, this exponential is a function of t, so nothing will affect this, right? So remember, they said u is equal to 0, right? So this is 0 is equal to, so cos 0, p times 0 is 0 and cos 0 is 1, right? So this is, I'm just left with d plus p times 0 is 0, sine 0 is 0, so this is 0 exponential minus c squared p squared t. So I can divide both sides by exponential minus c squared p squared. Divide both sides by exponential minus c squared p squared t. So d is equal to what? 0. So I can rewrite, so that's without my step 7. I can rewrite my solution u to be equal to, since d is equal to 0, so I will just be left with e sine px open bracket exponential minus c squared p squared t, right? So now we apply the second boundary condition, which says u l comma t is also equal to 0, right? Meaning that when x is equal to l, u is equal to 0. So I insert l here. So this is e sine pl, remember u is equal to 0, right, times exponential minus c squared p squared t. So right, so I divide, so the same thing applies here too. I divide both sides by this, divide both sides by this. So this is e sine pl equals 0, right? So now, so since e cannot be 0, remember d, the first constant d is 0, right? And I cannot just this is what I'm having, right? So the first constant d is 0, and I cannot just say, okay, remember this times this is equal to 0, right? So and e should not be 0. If e is 0, it becomes a trivial solution, right? So since I cannot make e to be equal to 0, I can make sine pl to be equal to 0. So sine pl is equal to 0, right? So before that, let us assume cp to be equal to pi. Remember, c was from the general form of the solution. Remember, we had c squared, right? So we assume c times the new constant we introduced to be equal to k. That's cp to be equal to lambda. So c was from the general form of heat equation. We assume it to be c. Remember, the general form of heat equation was d square u over dx square equals 1 over c squared du dt, right? So p was the constant we introduced for k, right, to be equal to lambda. Lambda is my eigenvalue, right? So this is what I'm assuming, right? So now let's continue from where we stop here. So since they are the value that can make a sine function to be equal to 0 are consecutive values of 1, 2, 3, 4 pi, right? So this can be written as so sine pl is equal to 0. That means pl is equal to n pi, right? N can be 1, 2, 3, where n is 1, 2, 3, and so on and so forth, right? So now since cp is equal to pi, so I make p subject of formula. So p is equal to pi over c, right? So insert it here. So this is pi over c l equals n pi. Remember, I'm looking for eigenvalues, right? So cp is equal to the eigenvalue. So making the eigenvalue here subject of formula. So eigenvalue is equal to c n pi over l, right? So since I've gotten my eigenvalue, so what do I do next? From this equation, before we substitute the value for p, since pl is equal to n pi, right? So p is equal to n pi over l. So we can also keep this one because it also come in handy, right? So this one is just basically calculated the eigenvalue, right? So but what we will need to continue our equation is this, right? So now, since p is n pi over l, so I'm going to substitute back into the equation for you. Okay, so there goes my step 8, substituting it back into the general form of the equation, which is u equals to e sine n pi x over l times exponential minus c square p square t, right? So now we can express this as a consecutive functions of u, meaning that when n equal to 1, let's call this u1, right? So this is e sine, let's call this e1, let's call this one e1 too, e1 sine 1 pi x over l, right? Exponential. Now since we assume cp to be equal to lambda, right? So c square p square will be lambda square, right? So this is the lambda square, and let's call this lambda 1, 2, and t, right? So there goes the same thing too. For when n equal to 2, this is u2 equals e subscript 2 sine 2 pi x over l, right? Exponential minus lambda 2 square t. So this continues as follows. So now we can express it as a general form. So expressing it as a general form, this can be expressed as u subscript r is equal to er sine r pi x over l, right? Where r is 1, 2, 3, 4, and so on and so forth. So open close bracket exponential minus lambda r square t, right? So now don't forget this has to be okay. Now this is the general form, right? So and if you can remember that if you are having consecutive solutions like u1, u2, u3 are solutions to particular u, that's less u1 and u2 are solutions to u, which is the function of x and t, right? So now this will be u1 plus u2 plus u3 and so on and so forth, right? So this can be written as summation of u, since this is 1, 2, 3, right? So this can be written as summation of ur, right? If u1, u2 are solutions of u, So adding the whole solutions together will give me my u, which is a function of x and t, right? So and this can also be expressed as a summation. So since my ur is equal to this, I can express it as summation e subscript r sine r pi x, right, over l exponential minus lambda r square t. So this is the solution. It looks like the solution of that's what exactly what we are looking for. This is exactly how our solution is like. This is exactly how our solution is. So now, but what is mixing here? We don't know the value of ER and we don't know how to calculate it. So now this is where our initial condition comes in. Our initial condition, which is that u x0 is equal to fx, right? So this is our initial condition, right? I know that I gave it from the beginning of the video. I said is equal to 0, right? But in fact in all cases is equal to a particular function x. Is always equal to a particular function x. So this is the initial condition, how it looks like. So right. So now we are going to apply our initial condition, right? So this initial condition, this means that when t is equal to 0, u is equal to a function of x. Now we're going to make t to be equal to 0 here. So this is u x t, right? T is equal to 0. Now if you can remember our summation, since it's going from 1, 2, 3, right? Where r is equal to 1, 2, 3, right? To infinity. So it's starting from r equal to 1 to what? Infinity, right? So this is summation r equal to 1 to infinity, right? E subscript r sine r pi x over l, right? Exponential. Now when I put t is equal to 0 here, this is exponential 0, which is equal to 1, right? So use x, that's u, which is when t is equal to 0 is function of x, right? So fx equals summation r equal to 1 to infinity e subscript r sine r pi x over l, right? So since this is 1, since exponential 0 is 1, so we have it. So now we apply for a rule of Fourier series, right? We can deduce the formula for ER, right? And this is when this is Fs, this is ER. And know that the only thing that is missing in our equation is E subscript R. So from our Fourier series, we know that ER is going to be, since the range is coming from 0 to L, right? The range comes from 0 to L. So since the range is coming from 0 to L, our Fourier series states that the ER will be 2 times the mean value. That's the mean value. The formula for mean value is 1 over L. It's going to come from 0 to L of fx sine r pi x over L. So this will be the formula for our ER. So ER is equal to 2 over L. It's going to come from 0 to L, function of x sine r pi x over L. So we've gotten the formula for our ER. So we can complete our equation to be our equation, which is u, which is a function of x and t, is equal to summation r is equal to 1 to infinity, open bracket, e subscript r sine r pi x over L times exponential minus lambda r square t, where ER is equal to 2 over L integrated from 0 to L of function of x sine r pi x over L. So you can either substitute here or you can leave your equation like this. So this is the final solution to what a typical heat equation will look like. So if you want to solve other questions on heat equation, then it's very easy. You can just if you can remember this final step, final solution, you can just substitute your lambda. Remember we said lambda is r is equal to c square p square, right? This is the formula for lambda. So this can be written as cp raised to power 2, right? So remember we use the constant c, right? From our general expression for heat equation, there was something like c raised to power 2. So if you are given, let's say, beta or gamma, you can just substitute it in the place of c, right? So if c squared is equal to beta, right? So c is equal to square root of beta. right? So just substitute here. So this is square root of beta squared times p squared, right? Then you can just substitute back here and you get your final solution. So you can be given fx2 from a typical question. Then this typically how you solve a heat equation. So thank you for watching, and please do so well to subscribe.